Welcome back, everybody. This is our third session in JEE Mains previous year question for chapter Atoms of class 12th. Before this video, we have made two videos in this series, and both of those videos are available on our channel's playlist section. We have a similar series for NEET also. So, friends, if you're preparing, then you can guide them through those videos. And if you find these videos helpful, useful, share them, subscribe to our channel, and want to donate us something, scan QR code in front of your screen. With this, let's start today's video. Now, in the previous one, I think we got it around 17 or 18. Yeah, this was the last question, question number 18. And today we will start with question number 19. In a hydrogen-like atom, when electron jumps from M to L shell, the wavelength of the emitted radiation is, I think it should be lambda. If the electron jumps from N to L shell, the wavelength of the emitted radiation will be. Now, this is a slightly different notation. We use this type of notation for cell or orbits in chemistry, where we have K shell as N is equal to 1, then comes L, then comes M, and then comes N, like this. So our initial radiation of wavelength lambda is for M to L shell. So this is the transition. So I can write that 1 by lambda will be equals to R into 1 by 2 square minus 1 by 3 square. So this will be 1 by lambda R, 1 by 4 minus 1 by 9, that will be 5 by 36 basically, and lambda will be 36 by 5R. Now going from N to L shell, so N to L shell, that will transition from 4 to 2. So for that, let's say we have wavelength is lambda dash, that will be R 1 by 2 square minus 1 by 4 square. Now when we solve this, what we will get lambda dash from this, that will be 16 by 3R. Now I can find the relation between them, that lambda dash by lambda will be equal to 16 by 3R, and multiply here 36 and 5R, and this will on, I think 4, yes, this is on 9, so this will be 20 by 27. So lambda dash will be 20 by 27 times of lambda. This is the relation we have, and that matches with option D here. Now in the next one, an electron from excited state of hydrogen atom emit radiation to come to the ground state. Let lambda n and lambda g be the de Broglie wavelength of the electron in the nth state and the ground state respectively. Let this is delta and be the wavelength of the emitted photon in the transition from nth state to the ground state for large value of n, where a and b are constant. So we have to find out relation between lambda and these constants a and b and lambda n squared. Now we know that for transition from nth state to ground state or 1, first state, we can write that 1 by lambda will be equal to R times 1 by 1 square minus 1 by n square, and this will be lambda n because we are transitioning from the nth level to the first level. Now what we can do, we can write like this, lambda n is equal to 1 by R, and that will be 1 minus 1 by n square raised to power minus 1. Now as already given that value of n is large, so this term can be this can be written as that 1 minus x raised to power minus n, and here x is very small. Why? Because n is large, so n square will be very large, so 1 by n square will be approximately 0. So we are replacing 1 by n square by x, that is very small. So this is basically we can use binomial distribution, binomial approximation, sorry. So this will become that lambda n is equal to 1 by r into 1 plus 1 by n square. This is the binomial approximation. Now, regarding de Broglie wavelength, this is for the nth state and this is for the ground state. And we know for regarding de Broglie that n times lambda n will be equal to 2 pi times Rn. Now for the ground state, n is 1 and lambda will be lambda naught. So we can write lambda naught is equal to 2 pi times R naught. And for the nth level, this will be same, and lambda n is equal to 2 pi Rn. And we can substitute value of Rn here. Rn is will be equal to so n square times R naught. So n lambda n will be equal to 2 pi n square times R naught. And from this n gets cancelled and we have lambda n is equal to n times 2 pi R naught. Now 2 pi R naught is basically lambda naught. So lambda n is n times lambda naught. So this is the relation, and we have already derived this in some previous question. So from this, what we have n is equal to lambda n by lambda naught. Now we will use it here. So this will become we have lambda n is equal to, okay, let me check for what we have to derive. Yeah, wavelength of the emitted photon. Okay, I made a slight mistake. What mistake I did? I use same notation. Means these are the this lambda node is the de Broglie wavelength. This lambda n is the de Broglie wavelength of the nth state. And here I also use the same notation. This is the wavelength of the photon emitted due to transition, and that is this delta n. So let me write this as delta n. So this is the relation for delta n, not lambda n. This is the correction we need to do here. So here delta n, which is equal to 1 by r into 1 plus 1 by n square. Now we will use n as this. So this will become 1 by r into 1 plus lambda n square divided by lambda naught square. Now I can write it like this, that delta n is equal to 1 by r plus lambda naught square by r plus lambda n square. Now this will be a constant a and this will behave like a constant b. So delta n is equal to a plus b by lambda n square, and that is the answer which matches with here option A. So option A is going to be the right answer. Now let us move ahead. If the series limit frequency of the Lehman series is V1, then the series limit frequency of the P fund series is. Now, what does this series limit means? This series limit frequency means the highest frequency. And when we have the highest frequency, when the second term, or in this formula, this is the formula for finding the wavelength. And when we will have highest frequency, when n2 will be equal to infinity, means we have the highest gap, means highest energy and highest frequency. So for Lehman series, n1 is 1, then comes the Balmer, then comes the Paschen. Okay, let me write it: Lehman, Balmer, Paschen, bracket, and then comes the P fund. So here we have 1, 2, 3, 4, 5. So in first case n1 will be 1, and in the second case n1 will be 5. So let's calculate for the Lehman series. For the Lehman series, wavelength lambda n will be series limit regarding frequency, that will be 1 by 1 by infinity. So from this 1 by L is equal to R, and from lambda L is equal to 1 by R. Now, if we want to convert it into frequency, then we know that frequency times wavelength is equal to speed of light. So that is basically assuming C here, assuming light is moving, or this photon is moving in vacuum or near vacuum. So from that frequency that is mentioned as V1 here, that will be equal to C by lambda, and lambda is 1 by R. So CR, that will be, so V1 will be equal to CR. Now let's calculate for the second case, that is for the P fund series. So 1 by lambda P will be equal to R into 1 by 5 square minus 1 by infinite square. So again, this term will reduce to 0, and we will have 1 by lambda P is equal to R by 25. And from this, we can write that lambda P is equal to 25 by R. Now, using the same relation, so for the P fund series, let's say frequency is Vp or mu P into lambda P is equal to C. So mu P will be equal to C by lambda P, that will be 25 by R. So RC by 25. And RC, this RC is equal to V1. So this is basically V1 by 25. So here it is. That is in option D. So option D is the right answer. Now move to the next one. The de Broglie wavelength lambda p associated with the electron orbit in the second state of hydrogen atom related to the ground state lambda g by. So here we have these are the de Broglie wavelengths, and regarding de Broglie wavelength, we know that n times the lambda n is equal to pi r n, and we have already devised the relation in the previous one that lambda n is equal to n times lambda naught. So here in the second excited state means n is 3, so lambda 3 will be equal to 3 times the lambda naught. Now for the third orbit, de Broglie wavelength is mentioned as lambda p. So lambda p will be equal to 3 times lambda naught, that is the de Broglie wavelength of the ground state, that is mentioned as lambda g. So that is lambda g. So lambda p is 3 times lambda g. That is option D. And how we derive this relation? It is available in the previous question here. Yeah, here it is. This is the full derivation. This is, you can rewind the video and see it here. So moving ahead, the energy required to remove the electron from a singly ionized helium atom is 2.2 times the energy required to remove electron from helium atom. The total energy required to ionize the helium atom completely is. Now let us first get the basic idea regarding this helium atom. So in helium atom, what we have, normally we have 2 proton, 2 neutron, and here we have 2 electrons. And as this atom has a 2 electrons, so we cannot directly apply Bohr's model. So Bohr's model is not applicable on this. But what if we eject 1 electron? So that is basically 2 proton, 2 neutron, and 1 electron. This is hydrogen-like element, hydrogen-like atom. This is singly ionized helium atom. So singly ionized helium atom behaves like a hydrogen-like element, hydrogen-like atom, and here Bohr's model is applicable. Bohr's model is applicable. So according to the Bohr model, if we find out ionization energy of this singly ionized helium atom, then it will be En will be given by formula minus 13.6 Z square by N square. For the ground state, so let's say Eg, it will be minus 13.6 into 2 square, that is the number of protons, divided by the first 1 square. So this will give us minus 54.4 electron volt. This is the energy required to completely ionize a singly ionized helium atom. But what we have asked, we have been asked to ionize a normal helium atom, not singly ionized, a normal helium atom. And we have been given the relation that energy required to remove electron from singly ionized helium atom is 2.2 times the energy required to remove the electron from helium atom. So if you want to remove electron from this helium atom, then let's say energy is E. Then this energy E will be equal to the energy required to electron from this singly ionized helium atom, that was Eg divided by 2.2. So that will be minus 54.4 divided by 2.2. And this will be equal to minus 24.73 electron volt. So what will be the process? First, we will eject one electron, and for the first electron ejection, we will need minus 24.73, or we have to give 24.73 electron volt, and then it becomes singly ionized helium atom, and then Bohr model will be applicable, and then we need 54.4 electron volt to eject the second electron. So total energy needed, E total, will be equal to 24.73 plus 54.4, and this is energy needed, so it will be in the negative, and this will comes out to be minus 79.13 electron volt. That is option B for us. Now in the next one, muon is negatively charged, where charge is equal to that of electron with mass 200 times of mass of electron, where m is the mass of electron and E is the electronic charge. If muon is bound to a proton and form a hydrogen-like element, identify the correct statement. So this is basically a muonic atom, where instead of electron, a muon revolves around the proton. Now, to solve this type of question, what you need to remember, the basic formulas derived in the Bohr model. So first case is given regarding radius. For radius, we have a relation that radius of the nth level is equal to n square h square into epsilon naught divided by pi me square. Or basically, we can write Rn is proportional to n square divided by m. Now for the same atom, or for the same, we can say, if we are discussing regarding the same orbit or the same level, then n does not, we don't need n. We basically check its dependency with only mass. As mass of the muonic atom is 200 times, as mass of the muon is 200 times more, mass of muon is 200 times the mass of electron. So due to inverse relation, the radius of the muonic atom will be 200 times smaller, as mass has an inverse relation here, and that is given in the option A. So option A will be the right answer. Now second, we have been given regarding speed, and how we can find out speed. Regarding speed, we can use centripetal force, that is mv square by r. As suppose this is proton and this is either electron or muon revolving, so this is a planet-like system. So here centripetal force will be equal to the attraction force or electrostatic force. So that will be 1 by 4 pi epsilon naught z e square by r n square. And this will be basically Rn. So here what we get, one of the Rn gets cancelled, and let's write this Rn, this whole expression, as some constant C by m, because we are only checking its dependency with mass only. So here this can be written as mv square is equal to 1 by 4 pi epsilon naught z e square divided by Rn. Rn is, let's say, C by M. So this M is also cancelled. So here these are constant, these are constant. So velocity is independent of mass here. So if it is independent, so velocity or speed does not change. So we can say statement B will be the wrong statement. Now coming to the C, ionization energy of muonic atom is 200 times more than the of a hydrogen atom. Now ionization energy En formula is minus Me4 divided by 8 epsilon naught square N square and H square. So E is directly proportional to mass. So if mass increases, ionization energy will also increase. So option C is the right answer here. And now moving to the option D, momentum of the muonic atom of the nth orbit is 200 times more than the electron. And we know from the Bohr's relation that Ln is equal to nh by 2 pi. And it is independent of the any mass. This h by 2 pi is constant and n is the orbit number. So if we are discussing regarding same orbit, then it does not change. So statement D is also wrong here. So we can say option A and C are the only right statement. So as per the given, none of these matches. And if we had to choose, then we will choose option D as it has both A and C. But D is the wrong one here. And now let me clarify one more thing here, that actually in all of these, whatever the formula I have used, let me use that separate color, that this Rn is basically actual formula for that will be n square epsilon naught by pi mu E square. What is mu? Mu is reduced mass. This is reduced mass, not the actual mass. Even in the energy term, this En is minus mu E4 divided by 8 epsilon naught square n square and h square. This is the reduced mass of the system, not the actual mass. And how we calculate the reduced mass? Let me show first for the hydrogen atom. So in the hydrogen atom, we have a proton and we have an electron revolving around it. So reduced mass of this system will be equal to 1 by mass of proton plus 1 by mass of electron. So if I compare it, MP, ME, here ME plus MP, and this is equal to 1 by mu. So from this, mu is ME, MP divided by ME plus MP. Now we know that mass of proton is very large as compared to mass of electron. So I can write it like this, that MEMP divided by MP common, ME by MP plus 1. This MP gets cancelled. And this reduced mass comes out to be Me into 1 plus Me by MP raised to power minus 1. And again, mass of proton is very large as compared to mass of electron. So this term is very small. So we can apply binomial approximation. So from that, this comes out to be 1 by 1 minus Me by MP. So this is the final expression. Now let's come to the actual values. So mass of electron is around 0.511 electron volt. Sorry, mega electron volt. And mass of proton is something around 938.6 MeV. So this term is basically zero. So in case of hydrogen atom, this reduced mass is basically equal to mass of electron, which we normally use. We directly compared it with the mass of electron and mass of muon. That's why we did this, because this reduced mass actually comes out to be very close to mass of electron. Now coming to this muonic atom. Now mass of muon is 200 times of the mass of electron, and mass of electron is basically half MeV. So mass of muon is 100 MeV. So if we again compare for muonic atom, this formula will be mass of muon 1 minus mass of muon by mass of proton. So this term will be again mass of muon into 1 minus 1 by 10, something like this. I'm approximating it. So again, this mass will be 0.9 times of mass of muon. So we can approximate again in that mass of muon, reduced mass in case of muonic atom will be again comparable to mass of muon. So this is the approximation which I have used while solving this question, that I have directly used reduced mass as mass of electron and as mass of muon. Now, if instead of this, if we don't have muon here, let me create this one, additional one. You can do it yourself. That suppose we have proton here at the center, and we have, and proton have positive charge, and we have a negative charge or anti-proton. We have an anti-proton revolving around a proton. Now, in this case, the reduced mass of this system, let's say this is proton system, so 1 by mp will be equal to 1 by mp plus 1 by mp, and reduced mass will come out to be mp by 2. So in this scenario, things will change. But in the above question, which we have discussed, reduced mass comes out to be approximately equal to mass of electron or mass of muon, and that's why we can directly use Bohr's formula without thinking about that how reduced mass will behave. So this is the approximation which you have to keep in your mind. Now with this, let's move to the next one. Some energy levels of molecules are shown in the figure. The ratio of wavelength lambda 1 and lambda 2 will be given by. So let me bring it on the one side. So we know that lambda is hc by E. So if we write for the lambda 2, then lambda 2 will be hc by E. This is the E, the energy difference between these two levels, and that is 1 by 3 E. So 1 by 3 E. So basically 3 hc by E. Now for lambda 1, it will be hc by the energy level, this difference, that is basically E. So now this will be, if we divide lambda 2 by lambda 1, what we will get? We will get 3. Or lambda 1 by lambda 2 will be equal to 1 by 3. So option B is the right answer here. Now let's move to the next one, 26, and this will be going to be the last question for today, I think. So the acceleration of the electron in the first orbit of the hydrogen atom. Now acceleration, as electron moves in a circular orbit, and we assume that it is moving with uniform velocity, proper circular orbit, so only it has a centripetal acceleration. Normally when some body revolves in a circle, then it has two acceleration, and its net acceleration is sum of centripetal acceleration plus tangential acceleration in the vector form. And we are assuming here that it is moving with constant velocity, so tangential acceleration is going to be 0 here, only centripetal acceleration will be there. And for that we can use basic formula, and that centripetal force mv square by r will be equal to the electrostatic force, and that is 1 by 4 pi epsilon naught into charge. And this is for hydrogen atom, we have one proton and one neutron, or one electron, so charge it will be E and E, so E square by R square. Now we know that centripetal acceleration is basically V square by R, so AC will be equal to 1 by 4 pi m epsilon naught into E square by R square. Now if we see in none of the option we have similar type of equation, so what we will do, we will substitute E here. We have to substitute E. Oh, so not E, sorry, we have to substitute R. So we know from the Bohr model that Rn is basically equal to n square h square epsilon naught divided by pi m e square. And we are discussing regarding first orbit, so n is 1. So from that r is equal to h square epsilon naught pi m e square. Now if okay, in the options we have r is also there, so and charge is not present, so we will substitute charge. So from this, charge is equal to e square is equal to h square epsilon naught by r pi m. So this will become 1 by 4 pi epsilon naught into 1 by r square into e square, that is h square epsilon naught r pi m. So epsilon naught gets cancelled and our relation comes out to be h square divided by 4 pi square m r cube, I think 4 pi square, yes, m times r cube. So I think, yeah, I forgot one term here. I forgot mass here, so m will be there, this will be m square. So h square 4 pi square m square r cube, that is option C. So option C will be the right answer here. And with this, we end this video here. Hopefully, whatever we have covered till now is helpful to you. Again, you have any doubts, suggestions, put them in comment section and like this video, then share and subscribe. Want to support us? Scan these QR codes. With this, again, thanks for watching and we will meet in next video.